Okay, so let's look at your homework from last night. You were working on 5-1. Specifically, I want to look at number 5 that you did last night in relation to a new program that I want to show to you. I want you to link the program NumInt from my calculator onto your calculator. So be sure you are passing that around and linking that. It's archived, so you're also going to need to unarchive it onto your calculator. And of course, you've got the calculator tutorials that tell you how to link and how to unarchive if you need that. Additionally, all right, so that program will make the types of things that we were doing on number 5 last night remarkably simpler. But let's look at number 5 for just a second. Last night on page 322, they asked you to estimate the area under the graph of f of x is equal to x cubed plus 2 from x equals -1 to x equals positive 2 using 3 rectangles and right endpoints, and then use 6 rectangles. And then they ask us to do the same thing with left and mid and kind of compare our answers, sketch the graphs, see what we got. So if we start with that equation, it was x cubed plus 2. We could do our change in x when we're doing 3 rectangles. Then we're going to do b minus a divided by 3, and our change in x would be 1. So the first subinterval would go from -1 to 0, then from 0 to 1, then from 1 to 2. So if we're using right-hand endpoints, we're going to plug in 0, 1, and 2. So that's what we've done down here. We plugged in 0, 1, and 2, and we got an estimate of 15. Now, if I sketch that graph, and I use the right-hand side of the endpoint to set the height of that rectangle, you can see I have a lot of overhang here. This is going to be a really high estimate. What will make that better is if I use more rectangles. So the second thing they told me to do was right-hand endpoints was 6. So we went through and we said, okay, if we do b minus a divided by n, that gives us a change in x of 1/2. So we can set each of our subintervals over here. And if I choose the right-hand endpoints, I'm going to start with -1/2 and then 0, 1/2, 1, 3/2, 2. So that's what we've got down here. We've plugged in -1/2, 0, 1/2, 1, 3/2, 2. And so we get a much better approximation. If you look at the graph, you can still see, though, I have some overhang like right here that should not be included, that's being included. So this is still going to be a high estimate. In actuality, I know the real answer to this is 9.75. So you can see 12 is better than 15, but it's still way high. All right? If instead we looked at this with left-hand endpoints, so for B we came down here and we did left 3 and left 6. So for left 3, if I come back up here to where we have the subintervals where we had 3, I'm using the left-hand endpoints of -1, 0, and 1. So I plugged each of those in, -1, 0, and 1. We got an area of 6. And if I sketch that over here, you can see if I'm using the left-hand side to set the height of this rectangle, it's going to be way low. Like I've got all this area right here that is not being included under that curve. So that's going to be a low estimate. What will make it better is if I use more rectangles. So then we went back and we did left 6. So if we come up here and we look at these subintervals that we created when we had 6 of them, and we use the left-hand side, we're going to start with -1, then -1/2, 0, 1/2, 1, and then 3/2. Notice we never use that last value of 2. So same thing down here, -1, -1/2, 0, 1/2, 1, 3/2. Plug those in, and that's a better approximation. Again, remember the actual is 9.75. So 7.6875 is better than 6. It's still low, though, but it's definitely better than it was. And the graph shows you that as well. I'm still missing some regions. That's why it's low, but it's a better approximation. If we go back then and we do midpoint, okay, so here were those same 3 subintervals. If I find the midpoint of each of those, if I do the midpoint of 3 rectangles, I'm going to use my midpoints as the x values that I'm plugging into the function. And this time, look how good that approximation is, even with only using 3 rectangles. I got 9.375 when the actual answer is 9.75. So that's a good approximation with only 3 rectangles. Midpoint definitely the way to go. So if I go back and I do 6, here are those same 6 subintervals that we were using. I'm going to create the midpoints for each of those and plug those in, and now I'm only off from my actual answer by 1/10, and I only used 6 rectangles. And again, you can look at the graph over here and see that's a good approximation. Now, how are we doing with that num int? Has it made it all the way around? No? Okay. For those of you that have had a chance to link that, you can do this along with me. If you haven't had a chance to link it, it's okay, because part of your homework tonight is going to be playing with that program. Alright, so what I'm going to do is I'm going to go to y equals on my calculator, and I'm going to type in that equation that we were just working with, x to the third plus 2. So go to y equals, if I can get mine to cooperate, go to y equals and type in x to the third plus 2. Alright, so then once I've got that in, I'm going to go to program. Alright, so once you get your programs to come up, if you'll choose number 6 right there, which is num int, and hit enter to run it. Again, we've already got the equation in y equals x cubed plus 2. It just graphed it there for me a second ago. I've got mine running in a Zoom 6, but whatever you've got your window on is fine. It's going to ask me for my lower limit. Now remember, our lower limit that we were using on that homework problem number 5 was -1, and our upper limit was +2. Now look at this happiness. I get to choose whether I want it to do left endpoints for me, right endpoints for me, or midpoints for me. We'll learn trapezoidal in Chapter 8 later on. So the first thing we were doing here was right. So I'm going to choose right. And then it asked me how many subintervals. So remember, you did 3 and then you did 6. What's really cool is when you get your calculator to do like 10 and 20 and 30 for you, and you can see those approximations get better and better. But I'm going to do what we did last night. I'm going to choose 3. It graphs it for me, which is so cool. You can see the 3 rectangles there. You can see the overhang as to why this is an overestimate. And see your little dancing dots over here? Remind you that this program is paused. So if I hit enter again, it'll unpause it, and then it tells me that that area was 15, and it's ready to go again. It says, hey, you want me to rerun it using different subintervals? So yeah, this time I want it to do 6, because remember, we did 3 and then we did 6. So I'll do 6 and then enter, and again it graphs it, and this time it shows me those 6 rectangles. And if I'll hit enter again, it tells me the area with 6 rectangles. And so I could keep going here if I wanted it to do the 10 or the 20 or the 30 or the 50 like we saw in the book yesterday. So it takes the tedium out of this for me and helps me be able to see the more rectangles that I use, the better I get to that actual area under the curve, and it does left, right, and mid. So last night, one of the problems that I asked you to do was 6C, but I asked you to wait until tonight until you had that num int program to use. So now you've got that and you know how to use that, so you'll be able to finish off 6C tonight. Okay? And you just second quit to get out of that program, and then you can go back into it. Alright, one of the other problems that you had last night was number 11, and I know it was your challenge, and so you may not have even done that one, but I want us to take a look at it for a second, because they love to give me something like this on the AP exam. I actually have an AP FRQ that I'm going to give you to work on a later night that covers this same type of a problem. So number 11 says, the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table, so find the lower and upper estimates for the distance that she traveled during these seconds. So since our speed is increasing steadily, that function is going to be increasing. So left 6 is going to give me a lower estimate, and right 6 is going to give me an upper estimate. So if I'm trying to calculate the distance, distance is just rate times time, and they gave me the velocity and the time in my table. So I could go through and I could create subintervals if I wanted to. Now, here's something that I want to caution you about. When AP does this, they don't always give us an equivalent change in x like this problem did. So I need to be very careful when I'm looking at an AP problem like the FRQ I'm going to give you. It won't be 0.51, 1.52. It might be 0.2, 0.7, 0.9, 1.3. It might jump all around. So you'll have to actually look at the change in x. You know, for instance, ours we do 0.5 minus 0 and we have a change in x of 0.5. But if this was 0 and then 0.7, you'd have a change in x of 0.7. And then if the next one went 0.71, you'd have a change in x of 0.3. So you'll have to look at that when it comes to an AP standard. They do not always use a consistent change of x. But then, of course, down here I can just use the rate times the time, and there's the first distance. Rate times the time, there's the second one, and the third one, and the fourth one. Sum all of those up, and that would tell me my distance. And of course, I've got the left estimate, which is low, and the right estimate that's high. I can maybe do an average of those two things to get a better estimate. And so I wanted to just run over that with you, even though that was our challenge, because that is something that we typically see. Alright, so let's look at section 5.2. We're actually going to look at this section for a couple of days, but we're picking up today on page 324. When we left off yesterday, we had defined our area under a curve as the limit as n approaches infinity, so we could have an infinite number of subintervals, an infinite number of rectangles, and we said that we could choose left endpoints, right endpoints, or midpoints, or any other value in that interval. And so that's what we were using this little star for. When we said f of x sub 1 with the asterisk up here, that meant choose any value in that first subinterval that you want, left, right, mid, or something else. And then we were multiplying it by the change in x, because that was base times height, so that was the area of the first rectangle, plus the area of the second rectangle, all the way down until we got to the area of the last rectangle. And we said another way to sum that up would be to keep that limit notation out in front, but we could write this as a summation. And the way that we would do that is we would use sigma notation to say the summation from 1 to n of f of x sub I. So that means start by putting 1 in here and stop when you get to n. So that would be f of x sub 1 plus f of x sub 2, f of x sub 3, all the way down until we got to our last one, and of course being multiplied times the change in x. So today they say, let's take that same notation that we finished off with yesterday that was going to be our definition of area under a curve, and let's define that as a definite integral. So on page 324, it says the definition of a definite integral is if f is a continuous function. That's like the beginning of everything we see now, right? It has to be a continuous function. If it's not, then everything else after that is irrelevant. If f is a continuous function defined between a and b, we divide that interval ab into n subintervals of equal width so that the change in x is equal to b minus a over n. We let x sub 0 be the a value and x sub n equal the b value. Those are the endpoints of the subintervals. And we choose sample points, x sub 1 star, x sub 2 star, x sub 3 star, to be any value in those subintervals that we want. Then the definite integral of f from a to b is defined by exactly what we see here. The definition that we finished with yesterday is going to be rewritten with this notation, and that will be our notation for a definite integral. All right, let's look at each piece of it. This first piece that we have is our integral sign. So it's the it looks like an elongated S to remind me that an integration is literally just a summation. A and B are going to be my lower limits of integration and my upper limits of integration. They tell me where to stop and start. F of x is my integrand, so my function is my integrand. And then dx always goes along with an integral sign. You won't see an integral sign without a dx along with it. So that's kind of the equivalence of what we had over here. This told me where to start and stop and to do a sum. So that's the same thing as my integral sign. This gave me the function that I was using, so that's the same as my integrand. And then we had our change in x on the end here, which is going to be very similar to a differential dx later on. But in essence, this dx goes along with our integral sign. This is also called a Riemann sum, named after Bernard Riemann, a mathematician and scientist. But anytime they ask me to do a left endpoint, a right endpoint, midpoint, or they say find a Riemann sum, it's the same thing. Alright, so not really a whole lot that we can do with these, but in example number 1 it says we want to express the limit as n approaches infinity from 1 to n of this function with a definite integral, and we want to use the interval from 0 to pi. So to begin with, I'm going to know that I start at 0 and I stop with pi as my upper and lower limits of integration. Then I need to find my integrand. And my integrand is just going to be my function. And if you'll notice, if I take off the subscript of I, that basically gives me the function for my integrand. So if I take off these little i's down here, I'm going to have x cubed plus x sine x, and that is my integrand. And then remember, we're always going to put that dx on the end because the dx always goes along with the integral sign. So that's how we could convert the notation from yesterday to the definite integral notation for today. Alright, the last thing that we want to look at today are some formulas that we're going to need. On page 327 in your textbook, they give you some formulas for evaluating integrals. The first three are formulas that we've seen before. The first one is our sum of integers formulas. So let's say that you wanted to find the sum of the first 100 numbers. Instead of doing 1 plus 2 plus 3 plus 4 plus 5 plus say all the way up to 100, all I would have to do is say, look, I'm trying to find the sum from 1 to 100, so I'll put 100 in the place of n. So that would be 100 times 100 plus 1 over 2. 100 times 101 divided by 2. If I were trying to find the sum of squares, that would be like the sum of the first 15 squares, like 1 squared plus 2 squared plus 3 squared plus 4 squared. Then I could say, okay, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4, all the way up to 15 squared is 225. Instead of having to do that, since 15 is in the place of n, then I can just come over here and say that's going to be 15 times 15 plus 1, 16. Times 2 times 15 plus 1, 31. So I'll have 15 times 16 times 31 divided by 6, and that would give me the sum of those squares. Sum of cubes formula, same idea. If I wanted to find the sum of the first 10 cubes, that'd be like 1 cubed plus 2 cubed plus 3 cubed all the way up to 10 cubed. I can just put 10 in the place of n, and so that's going to be 10 times 10 plus 1 over 2 whole thing squared. So 10 times 11 over 2, that whole thing squared, would give me that sum. The last couple of properties that we have down here will make finding summations a little faster and easier. The first one says if you have the summation from 1 to n of a constant, then it's going to be n times that constant. For instance, if I had the summation from I is equal to 1 to 5 of the constant 7, it's the same idea as let's say that you are graphing y is equal to 7 and you make an xy chart. It doesn't matter what you put in for x, you're going to get a y value of 7. So you can put in some crazy random thing and you still get a y value of 7. The reasoning behind that is there is no x in this equation to put a value in for, so it does not alter that 7. The same concept is going on when I have a summation of a constant. This says put 1 in for I. I don't have an I, so it's completely unaltered. I just get the value of 7. So when I plug in 1, I get 7. When I plug in 2, I get 7. When I plug in 3, I get 7. Plug in 4, plug in 5. So instead of sitting here writing this number over and over again, however many times I have for n, it's a whole lot faster to just say, take n, the number of times you're going to write this number, and multiply it by your constant. So you can see if I would have just done 5 times 7, I would have gotten that 35. So this summation of a constant will make things a lot faster. The next one they give me is if you have the summation of a constant and times a value, you can move that constant out in front and then do your summation. And when you're finished with the summation, multiply by the constant at the end. The next one they give me is, actually they write it as 2 separate formulas in the book, and I've combined it into one, and that is the summation of 2 things being added or the summation of 2 things being subtracted. So let's start with adding. If I have the summation of 2 quantities are being added together, I can break that into 2 separate summations and find the first one and then add the second one. If instead of this plus sign I had a minus sign, if this was the summation of one quantity minus another, I can make that the first summation minus the second summation so that I break it apart. Now, not a whole lot to do on this tonight, so just a couple of these problems. On pages 334 to 335, we're doing 5, 15, 17, challenge number 9. And then remember that I also want you to go back and practice on number 6C from last night using that Num int program that we played around with today.